So my name's Craig Heffner. Yay. And obviously, I'm going to be talking about hacking routers today. Specifically, what I'm going to be discussing is how an external attacker can gain access to the internal administrative web interface of your common residential gateway router. Before I start, though, oh, this is the wrong slide set. Damn it. Oh well. Before I start, though, my work did ask me to make a couple statements. First of all, I'm not doing this on behalf of them. I didn't do any research on behalf of them. I'm not here as part of my work, so if you know who I work for, stop calling them and emailing them. But I decided to focus on router security because there's very little security in home routers. I couldn't fit very many screenshots into this slide. I had about 17 more. And all of these vulnerabilities typically are only exploitable from the LAN, because most of them, end up being in the web interface, which typically most people don't have remote administration enabled. So the question for an attacker is not how do I attack these devices and hack them. The question is how do I get access to the device if I'm not on the LAN? And so the answer to that is typically either cross-site request forgery or DNS rebinding. And request forgery is really popular because it's very, very easy to do. But it has a lot of limitations, especially when you're going after routers. So first of all, you can't rely on there being a trust relationship between an internal client's browser and the router, because no one ever logs into their routers. So you can't exploit that. You can't forge basic authentication logins anymore with cross-site request forgery. You used to be able to do, user, password, @ and then the URL. Now, that doesn't work anymore. IE doesn't even recognize that as a valid URL, and Firefox will actually throw a warning to the user. So you can't rely on that either. There's also some anti-cross-site request forgery mechanisms in some routers. This Action Tech router is one, actually, that I'll be demoing later. And ultimately, cross-site request forgery is limited by the same origin policy in the browser, and it always has been. So if you're not familiar with the same origin policy, basically what it says is, okay, if I browse out to attacker.com, I load up some JavaScript from attacker.com. That JavaScript can interact with any page on attacker.com, but it can't interact with google.com or 192.168.1.1. And that's good because you don't want some random person's JavaScript talking to your router. So that's where DNS rebinding comes in. The premise behind DNS rebinding is basically, okay, well, if the browser is going to implement security based on the domain name, that's fine. Just tell it that attacker.com has switched IP addresses to 192.168.1.1. So now when the attacker's JavaScript connects back to attacker.com, the request actually goes to your router. But DNS rebinding has been around for a long, long time. It's like 1996 called and wants this exploit back. It's been around forever. And so people have put in preventions to stop it, or try to stop it anyway. And so browsers have put in patches, and third-party plugins have put in patches. And you also have services and tools like OpenDNS, NoScript, DNSWall, DNS Mask also has some anti-rebinding stuff in it. And these all attempt to stop people from using DNS rebinding to attack your internal network. And the way they do that is they say, well, no external domain should resolve to an internal RFC 1918 non-routable IP address. Because if it does, you're probably not going to be able to connect to it anyway. And if they're doing something malicious, then we want to block it. So that's basically how these tools work. So I'm going to focus on using the multiple A record attack, which is one variation of DNS rebinding. And if you're not familiar with it, really all it is DNS load balancing. That's it. You return multiple IP addresses for a DNS lookup. And so pretty much any major site does this. You do a DNS lookup on Google, you get 5 or 6 IPs back. So what happens is the browser says, okay, you have 3 IP addresses, that's fine. And it just tries and connect to each IP address in order. And if one of those IP addresses goes down, that's fine. I've got more IP addresses. It switches over to the next IP address in the list. This attack is limited, though, in that you cannot target internal IP addresses with this. You can target any public IP you want, but you can't go after internal IPs. So let's take a look at using this attack to go after a public server. So you've got your attacker out there with an IP address of 1414, and he wants to send some malicious content to the web server on 2358. Now, he doesn't want his IP address showing up in the logs for whatever reason. So he's going to proxy his requests through this client who's feeling very safe sitting behind his router. So the attackers register the domain name of attacker.com, and he convinces this client to browse out to attacker.com. So the first thing the browser does is a DNS lookup. It says, what's the IP address for attacker.com? So the attacker's DNS server then says, oh, I actually have two IP addresses, 1414 and 2358. Now, 2358 is obviously not the attacker's IP address, but the browser has no way of verifying that. So it just says, okay, you've got two IP addresses, I trust you. So it's going to try the first IP address first, which is 1414, does its GET request to the attacker's server, and the attacker sends back some JavaScript code. Now that JavaScript code then initiates a request back to attacker.com. And the browser says, well, you came from attacker.com, you're going back to attacker.com, fine, that's allowed. But when the browser makes this connection to initiate the request, the attacker server sends back a TCP reset packet. So now the browser says, well, crap, that server's down. I better switch over to the second IP address. And so now the attacker's JavaScript is interacting with the 2358 server. He can send GET requests and get the response back, parse the data, and even send it back to the attacker if he wants. So this works. This has always worked. There's never been anything to stop this from happening. And there's certainly security issues that arise from this. But the real threat has always been attacking the internal LAN. So I don't want to go after some public web server. I want to go after the client's router. I want to get access to the router's internal interface. So this is the same scenario, but instead of attacking a public IP, the attacker is going to try and rebind to 192.168.1.1. So again, client does a DNS lookup. And again, the attacker server sends back two IP addresses. Now, the browser says, oh, you've got two IP addresses. Oh, but one of them is an internal non-routable IP address. And the browser will always try internal non-routable IP addresses first, regardless of the order in the DNS packet. So he's just going to go and send the request to the router and load up the router's web interface in the client's browser. This does the attacker no good because the client never went out to the attacker's web server to get his JavaScript. So the attacker has no presence in the browser. He's accomplished nothing. So the problem here is that everyone's focused on protecting internal IP addresses. Okay? Routers are kind of unique. They have both an internal and an external IP address. And so we can actually attack the external IP address using this method and gain access to the internal interface. And the reason that works is actually kind of interesting. So if you take a look at a netstat on a router, and this is actually from an OpenWRT router, take a look at how it's binding services. These services are bound to every interface on the router. So port 80, yeah, that's bound on your WAN interface. It's listening on the WAN. Now, what prevents just anyone on the internet from connecting into the router are your firewall rules. Now, anyone who's looked at OpenWRT's firewall rules knows this is extremely simplified. But basically it says, okay, ETH0 is my WAN interface. I don't want people connecting in from the WAN. So anything that comes in on ETH0, drop it. Everything else we'll accept because that's our internal interfaces. That's fine. And there's nothing really inherently wrong with this. But like the same origin policy, this attempts to enforce security based on a name. Computers don't work on names. They work on IP addresses. And where this comes back to bite us is when you look at how the underlying operating system handles IP packets. RFC 1122 defines two different models for implementing an IP stack. One's called the strong end system model, and one's called the weak end system model. Now, if you know nothing about these two models other than the names, which one do you think is better? Right. But interestingly enough, the weak model is actually the more prevalent model of the two. It's implemented by Linux, BSD, I believe Solaris, and even previous to Windows. So let's take a look at how this works. This is verbatim from the RFC. You can read it if you want. RFCs are very boring. But all this says is, okay, if I'm a router or any computer, and I receive a packet, I'm going to look at the destination IP of that packet. And if the destination IP matches any of my IP addresses on any of my interfaces, I will accept that packet and process it. Now, it could come in on technically the wrong interface. So it could come in on ETH0 and it matches the IP address on ETH1. Doesn't matter. I'll accept it and process it because obviously this is one of my IP addresses and this packet's intended for me. So let's take a look at how this works in the context of the router. Okay, again, we have an internal client, a router, and the internet. So the router has two interfaces. ETH0 is its public WAN interface, and ETH1 is the internal interface. Now, ETH0 has an IP address of 2358. That's the router's public IP. So what happens when an internal client tries to browse to 2358? Well, he's going to send a TCP SYN packet. And the router's going to look at this and say, well, the destination IP is 2358. That's one of my IP addresses. Awesome. And it goes, okay, the destination port is port 80. Well, hey, guess what? I have a service bound to port 80. Because remember, those services bind to every interface. So he says, yeah, I have a service listening on 2358, port 80, and 2358 is my IP address. So I'll accept this, complete the three-way handshake, and so now the client can actually access the router's internal web interface via the public IP. So, oh, wait a minute. What happened to that firewall rule? Remember, we had a firewall rule that says block everything on ETH0, right? Well, if you take a look at the traffic, the top window is ETH0 and the bottom window is ETH1. No traffic ever went over ETH0. The weak end system model logic happens pre-routing. So everything gets accepted and processed on the internal interface. So that firewall rule that we had that says block everything on ETH0 does nothing because there's no traffic on ETH0. So ultimately, an internal client can punch in the public IP and get the web interface. Now again, this by itself is really not a problem. It's not a vulnerability per se. But I, as an external attacker, can rebind any internal client to any public IP I want, including the router's public IP. So now, if I can do that, I can completely bypass all of these protections that are trying to stop me from rebinding to internal IP addresses, because I'm not rebinding to an internal IP. So let's take another look at our rebinding attack. Again, same scenario as before. But this time, instead of rebinding to 192.168.1.1, attacker's going to rebind to 2358. So internal client does a DNS lookup, and again, the attacker's DNS sends back two IP addresses. The browser looks at that and says, hey, you've got two IPs, they're both public IPs, that's fine, I'll try them in order. Goes out to 1414, gets the attacker's JavaScript. JavaScript initiates connection back to attacker.com. So the browser goes back to 1414 because that's what worked before. But this time, he gets a TCP reset packet back. And so now he immediately switches over to 2358. And now the attacker's JavaScript has full interactive access to the router's internal web interface. So this is a really, really nice attack for DNS rebinding. Because unlike some other DNS rebinding attacks, there's no delay or waiting period before you can rebind. It's pretty much instant. We also don't need to know the router's internal IP address. That's always kind of a problem because, routers can have different internal IPs and people can change the IPs, and we don't care because we're rebinding to the public IP. Another nice thing is this works in all major browsers because this is just how browsers work. It's how they handle DNS redundancy. The downsides are we have some very specific requirements on the router. Okay, we basically have three specific requirements. Okay, the router has to bind its services to the WAN interface. The firewall rules on the router have to block based on interface name and not destination IP or some similar configuration. And the router also has to implement the weak end system model. So obviously not all routers are going to be vulnerable to this. So the question is, which routers are? So I tested 30 different routers, and out of those, 17 were vulnerable. And that includes routers from Asus, Belkin, Dell, which I didn't even know they made routers, but apparently they did. Thomson, these are actually pretty popular over in the UK, pretty popular DSL routers. And one thing I wanted to test, I didn't get a chance, is the BT Home Hub, which is really popular in the UK, and is basically a rebranded Thomson. So those may be vulnerable as well. Lots of Linksys. Lots and lots of Linksys devices. And I really like this slide because the bottom two routers there, the 54GL and the 160, are on Amazon's top 5 most popular selling routers list. So awesome. Of course, a lot of people put third-party firmware on their Linksys routers, and it works against them too. Now, hopefully, you have some other security stuff put in place, which we'll talk about later if you're running these, but not everyone does. My favorite, though, are the ActionTech routers. And a lot of people might not have heard of ActionTech because they're not really a big router name. But these are the routers that Verizon Fios and Verizon DSL customers get. So these are everywhere. Let's see, the ActionTech 701, 704, and then 2 versions of the MI424WR. All of those I tested, and it worked against all of them. Now, what's really interesting about these, the one on the far right there, and on the bottom, they're both the same router, just different hardware versions. What's really interesting is the firmware running on these isn't manufactured by ActionTech. ActionTech actually uses a commercial third-party firmware called OpenRG, which is made by a company called Jungo. And Jungo claims that this same firmware is deployed in over 23 million households worldwide. So awesome. I like that. So this attack definitely works, but we need to make it practical. Okay, you can't just say, oh, my JavaScript can see your router's internal interface. People go, yeah, okay, whatever. I don't care. So we have to make it really a practical drive-by attack, really to demonstrate what can be done with this. Okay, so we have to get the target's public IP address automatically, because we don't want to have to know that beforehand. We want to be able to get that automatically. And it seems kind of simple at first, but we have to know this before they ever do a DNS lookup on us. So we basically have to know their IP before they come to us. And that it actually is a simple fix for that. The more difficult part is we have to coordinate all our services. So the DNS server, the web server, and the firewall all have to be coordinated. They all have to know what state each client is in. They all have to know when to block a client, when to allow a client, what IPs to return to each client. So that requires custom code. And so that's a little bit more difficult. And finally, like I said, we have to make it do something useful. So to that end, I wrote the cleverly named tool Rebind. Yay! So it basically does everything for you, except register a domain name. It's pretty much //run, and you're done. It implements a DNS server, web server. It interfaces with the IP tables firewall. It's got an HTTP proxy for the attacker to use. It serves up JavaScript code, which basically acts as a client-side proxy to proxy requests from the attacker to the router and back. I tried to make the JavaScript as quiet as possible, so it supports cross-domain XML HTTP requests for exfiltrating data, if that's supported in the browser. IE 8 and Firefox 3, 5, and later support those. And I've tested it in all major browsers, and it works. It's quite nice. So here's how Rebind works. I love the robot devil. He's the best. So you've got an attacker here, and he's sitting behind the 1414 server, and he's running Rebind on that server. And he wants to target this client's router. Again, the client's router's public IP is 2358, and the attacker's domain is attacker.com. So the attacker gets the client to browse to attacker.com/init, I-N-I-T. So again, before he does this, he has to have the name server set up, and Rebind has to basically handle all of your DNS queries, because Rebind's handling the DNS portion of the attack. So the attacker, before he gets the client to browse, he has to go into his registrar, wherever he registered his domain name, and register a name server. Just name it ns1.attacker.com and put in the attacker's IP address. And then once that's registered as a name server, he has to go into his domain's configuration and say, hey, ns1.attacker.com is the primary name server for my domain. But that's all the configuration you have to do. So once the client browses out to attacker.com, of course, it has to do a DNS lookup. And Rebind's only going to send back one IP address. Because again, remember at this point, we don't know the client's public IP. We have no idea what it is. So he's just going to say, yeah, I'm at 1414. So the browser browses out to 1414 and requests /init. Now we have the client's public IP, because he's made a direct TCP connection to the web server running on Rebind. So Rebind says, okay, I've got your public IP of 2358. He then sends back a randomly generated subdomain redirection. So he randomly generates whackme.attacker.com /exec, and he redirects the client to that. Now he logs this so the DNS server knows as well. And so now the browser says, okay, this is a 302 HTTP redirect, that's fine, but this is a new domain, so I have to do a new DNS lookup. So it says, okay, where is whackme.attacker.com? And so now the DNS server says, aha, the web server just redirected an IP address of 2358 to whackme.attacker.com. So if you're requesting whackme.attacker.com, you must be 2358. So at this point, it sends back the two IP addresses, 1414 and 2358. So again, the browser's going to try 1414 first, requests the /exec page, gets the JavaScript, and now once Rebind does this, it's going to tell IP tables, hey, reject any connection on port 80 from 2358 with a TCP reset packet. So when that JavaScript attempts to connect back to attacker.com, he gets a TCP reset from IP tables. So now he switches over to 2358, and we've rebound attacker.com to the router's public IP successfully. Now once this happens, the JavaScript is going to start sending requests, pull requests, back to attacker.com on port 81. Because remember, he's blocked on port 80, so it gets sent to port 81. And basically, this pull request is the JavaScript saying, what do you want me to do? Well, at this point, Rebind doesn't have anything for him to do, so he sends back nothing. But once these pull requests start coming in, the attacker's web interface has that client's IP address in there. Yes, I know that's not the same IP address, but that's okay. So all the attacker has to do is click on that IP address. And when he does, he has his browser configured to use the Rebind HTTP proxy. So his request actually goes off to the Rebind server. And Rebind says, okay, you want me to do a GET request on the index page of 2358. No problem. So he holds that connection open to the attacker's browser. And the next time this pull request comes in from the JavaScript, he says, yeah, I got something for you to do. Do a GET request on the index page. So the JavaScript says, all right, no problem. Sends a GET request to whackme.attacker.com, which is the subdomain that we rebound. Gets the response, sends the response back to Rebind, and then Rebind forwards that back to the attacker's browser. And so now the attacker is browsing around inside the router's web interface as if he's on the LAN. And he can click on links and submit forms and do whatever he wants. So this is much more fun when you do it as a demo than sitting down and explaining everything. So let's see if I can get a demo going here. I will smack you, Will. All right, so Rebind's running. And yeah, that's it. You just run it. There's no configuration beyond that. It does support a bunch of command line options if you want them. So this is my browser as the attacker, and I've already configured it to use Rebind as my proxy. So if I type in Rebind, I should get the web interface for Rebind. And let me full screen this so it fits a little better. There we go. So now I've got an attacker over here who's connected to the internal LAN of this router. So I'm going to have him browse to attacker.com/init, and he should pop up here. There we go. So now as an attacker, I just click, and I'm in. So this is the login page for Verizon Fios routers. The default login is admin, password 1, and no one ever changes it. Oh, that's not good. I knew my demo would fail. Yeah, apparently my client stopped calling back, or something terrible happened. I swear this works. Yeah, so he stopped calling back, and I have no idea why. Let's try again. When in doubt, try again, right? All right, so he's back. Yay! Okay, so we logged in. So what I'm going to do now is I'm going to go ahead and just enable remote administration. Oh yes, I do want to proceed, thank you. So go down here to remote administration. Yes, I want to proceed, guys. This user interface is so annoying. Okay, so I'm going to enable remote telnet. Yay, okay, we're done. We've enabled remote telnet on this guy. Now, you will notice here that the images don't get displayed. That's because Rebind blocks image requests, because I don't give a crap about images and they eat up a lot of bandwidth. So now, we should be able to, if my terminal comes up here, telnet 2358, login same as before, admin, password 1. And you get this weird wireless broadband router thing. Just type in shell, and you get a root shell. So a lot of people say, well, I get into your router, I'll change your DNS settings. Yeah, I hate that. That's stupid. I don't want to do that. I want to own your router. So yeah, I've got a root shell now. I can do, ARP. Be like, oh, there's an internal client. Now I know his IP. The downside to these things, of course, they're running Linux, but it's really stripped down. You don't have netcat, you don't have wget, you don't have all these fun things. But you do have TFTP. So I've cross-compiled a scanning tool to run on the IXP 425 processor that's inside this router. So I should be able to TFTP it down here and just start attacking the internal LAN. Okay, so there I got it. Let me chmod it real quick. Okay, so again, this is kind of a real quick thing I threw together, a poor man's netcat that runs on the ARM processor, because I had trouble cross-compiling netcat for some reason. But let's just go ahead and scan that internal IP address we got from the ARP. 192.168, 1.3. Yeah, if I type in the right IP, it would probably help, wouldn't it? And let's scan ports 21, 22, 23, 80, and 443. Oh, that was quick. Port 80 is open. So we can now do a quick GET request to port 80 on this internal server. And yeah, we get the secret web server page. Fun. So once I'm into your router, I can now go ahead and put whatever tools I want on this thing and run them against your internal network. I mean, I'm on your internal network at this point, which is the great thing about routers. They're connected to the internet and your LAN. Fun. So really, I can turn this into an attack platform to go after your entire internal network at this point. And of course, routers don't have any kind of antivirus or anything on there, so I'm pretty much do whatever the hell I want. But we're not limited to attacking the main web interface of the router. So again, you notice, okay, I had to log in, and yeah, most people are going to leave the default login. So that's a big problem. But I can also go after SOAP services. What about UPnP? UPnP lets me open up ports on your router to any internal client without any authentication at all. I can interface with UPnP using JavaScript. It's awesome. There's also HNAP, which I'm not going to go into, but HNAP is the Home Network Administration Protocol, which some routers implement. It does require authentication, but I've found some issues with certain implementations that allow me to get around that. We can also rebind to any public IP. We're not restricted to the router's public IP. So the rebind tool allows you to say, hey, I don't want to rebind to this guy's router. I don't really care about his router. I just want to use him as an on-demand botnet to attack this other server over here. So here's a list of IP addresses I want you to rebind clients to, and then the attacker just has a script that goes through and attacks those servers through someone else's web browser. So how do we stop this? Force fields would be awesome. Unfortunately, I don't have those working yet. Luckily, it's fairly easy to stop and to identify. So, first of all, if you can punch in the public IP of your router as an internal client and you get the web interface, yeah, this will work. Yeah, there we go, next slide. Now, once you identify that this works, the best way to stop it is to break any one of those 3 requirements we have on the router, okay? So you can stop the way stuff binds to interfaces, you can change firewall rules, you can change routing rules. Of course, just disabling the HTTP interface is probably the best thing to do anyway. We can also do that. And then we can also reduce the impact of the attack with just basic security precautions. So if you want to block the attack of the router, you can potentially tell the router services to bind to specific interfaces. Not all routers let you do this, and most people will not have the technical skill or the access to the router in order to do this. So it's probably not the best option, but if you can do it, that's really the best way to do it. You can also reconfigure the firewall rules, and these are, again, IP tables rules. It basically says, okay, my internal interface is ETH1. If someone on ETH1 tries to go to my public IP, drop it. Now, the downside, you notice I put in actually /16 here. The downside to putting in your specific public IP is that as soon as it changes, this rule breaks and you have to update it. So instead what you should do is do a whois lookup on your public IP for your ISP, see what the range is that they're handing out for DHCP, and just block that entire range. Because unless internal clients are trying to like hack your neighbors, which hopefully they shouldn't be doing, then this won't really affect any kind of internet connectivity that you have. You're just blocking everything in the DHCP range that comes from your ISP, and then you don't have to update the rule. Yeah, don't use HTTP. Use HTTPS at least. Because if I try and rebind to HTTPS, you're going to get at least a cert error, and that's going to break the attack. Now, if you're administrating a router, it's best to use SSH. Even Telnet is better than the web interface. Most people can't do that, though, so best suggestion is just disable HTTP and enable HTTPS. Also disable UPnP while you're at it. Yeah, I know you need it for your Xbox, you need it for your Skype and all that other crap. It's bad. Don't use it. However, there are some problems. Don't just enable HTTPS and leave HTTP enabled, because then I can still get to HTTP. Some routers actually don't let you disable HTTP. I've seen routers where there's a checkbox to enable HTTPS, and you can't disable HTTP at all. So that's a problem. Some routers have HTTP services listening on alternate ports. This router, for example, listens on both port 80 and port 8080. So if you're disabling this, make sure that all of those ports get disabled. Again, I'm bringing up HNAP. It's a Home Network Administration Protocol. It uses HTTP, not HTTPS, and in some routers, you cannot change that, and you cannot disable it. So I can still go after that if you have a weak password. Blocking attacks on the host. Let's say you don't have access to your router to do this. You just don't have sufficient access to make these changes, or you don't want to make the changes for whatever reason. You can go around to all of your internal hosts and basically put in the same rule. Say, don't allow this host to browse out to the router's public IP. Because again, I need an internal client in order to do this attack. So if the internal client can't access the router, then it breaks the attack. The downside to this is you have to do this on every single device that connects to your network and will ever connect to your network. That includes your iPads and your iTouches. So that can certainly be a management nightmare if you have, more than 2 or 3 computers. You can also configure dummy routes as well. Just say, hey, route everything that's going to my public IP to loopback. And of course, the connection will never succeed. Basic security precautions. For God's sakes, change your router's default password. No one does this. Hopefully everyone in this room does this, but many people don't. Keep your firmware up to date. There are a lot of vulnerabilities in these routers. If you go online and you have a router and you're like, oh, there's no vulnerabilities in it, that means someone hasn't looked at it close enough yet. I'm serious. These things are full of security holes. So make sure you keep your firmware up to date, because there's probably a vulnerability out there, and if something gets published, you want to make sure you have a patch for it, assuming your vendor actually patches it. And don't trust untrusted content. And yes, everything on the internet is untrusted. You cannot trust stuff on the internet, especially something called attacker.com. I would suggest disabling JavaScript or using no script. But to be honest, that's completely impractical for the average user. I get so annoyed browsing around the internet without JavaScript, and it's like, God damn it, I just enable it anyway. Because it's so annoying. Everything uses JavaScript, and stuff will just break epically if you don't have JavaScript enabled. So if you want to do that, knock yourself out. But again, it's not really a good suggestion for the average user because they're not going to do it. So vendor and industry solutions. So fix the same origin policy in the browsers, please. This attack has been around for almost 15 years. So I know you notice that I don't have fixed DNS up here. I know a lot of people say, oh, we need to fix DNS, we need to fix DNS. This is not a DNS problem, and I think it's completely unfair to put the burden on DNS. Okay, DNS was around long before the same origin policy was. DNS was never intended to be used for security, but whoever decided in their infinite wisdom to create the same origin policy said, we're going to take DNS, which is a completely unauthenticated, unverifiable, unsecure protocol, and base a security model on it. So the problem is with the same origin policy in the browser, and that's what needs to be fixed. If you're a router vendor, implement the strong end system model in your router. End users will not know or care. It will not break anything for them, and it will keep them secure from this particular attack. You can also build DNS rebinding mitigations into routers. The only router that I know of that does this is pfSense, because when they saw this posted up on the Blackhat site when the talk got accepted, and they contacted me, I said, yeah, just check your HTTP host headers. Make sure the HTTP host header has your host name in it or IP address and not someone else's. And so their actual their beta release for the 2.0 release of pfSense has that check in it. So kudos to them. But no one else does this, to my knowledge. And that's a very, very simple way to stop any DNS rebinding attack in its tracks. So, how am I doing on time, by the way? How many? 20? Wow. I hope you guys have a lot of questions. I went through that a lot faster than I expected. So DNS rebinding still poses a threat to the LAN, even with all the security protections out there and things that people have put in, because ultimately, what they've put in doesn't work. It's like going to the doctor and saying, hey, I have diarrhea, and he gives you a cork. It's not a real fix. We have tools available to exploit DNS rebinding. Okay, they work. Well, they work the second time at least. And really, you are ultimately responsible for the security of your network. You need to be aware of this stuff. I know a lot of people start talking about DNS rebinding like, what the hell are you talking about? Seriously, Will. I'm going to smack you. Yeah, so make sure that you have this, you know about this stuff, and you take the proper precautions. Because, I mean, you really can't rely on vendors to fix patches in their routers. I mean, if you have a router that's like, you know, they dropped support for it a month ago, they're like, oh, well, you just have to buy a new router. Darn. So make sure you're aware of this stuff. There is stuff that you can do to stop this. Make sure you do it. So with that said, the rebind code is going to be posted up on rebind.googlecode.com. I don't have the code checked in yet, but it'll be up there sometime today. If you want to contact, again, do not contact my work. Contact me. And do we have questions?
JavaScript, as you mentioned, I guess that's on the client machine.
Yes.
That feeds the router's interface to your. I'm sorry. My question was the JavaScript that you said you had on the client, that you put on the client, that feeds the router's web interface to your attacker machine?
Yeah, it proxies requests from the attacker to the router and back. So it does that pull request back to rebind, and then rebind tells it what to get. It gets from the router and then sends it back.
Okay.
One question? Yeah. No more? Oh, there we go. So Fios is, the problem with Fios is they use Mocha for their cable connection. So you have to have a Mocha-enabled router, and those are not very prevalent. So most people just use the action tech. Supposedly you can get them into bridging mode where they just pass through, but everyone I've talked to who's tried that is like, it's a big pain in the ass and it never worked. So pretty much everyone on FiOS is using these routers with very few exceptions. Okay, yeah, so if you have, let's say you have the action tech, okay? The action tech router is your border gateway, and you put another router behind that, doesn't matter. I'm still attacking the public IP of the action tech. So I can still access the action tech router. Yeah. It'll help protect your internal IP once I get on the router, but it won't stop me from getting to the router. Right. Yeah.
One of the manufacturers you listed was Linksys. We know who the parent company of that is. I'm kind of surprised that they haven't contacted you.
My work told me that they contacted them about something, and then I never heard anything back from it. So I don't know if they just gave up or what happened with that. Again, simply because my work was listed on the presentation, everyone contacted them instead of me. But yeah, I haven't heard anything from them specifically. And again, this isn't really a problem. I guess it's kind of a problem with the routers, but there's no real vulnerability in the routers. It really needs to be fixed in the browser, ultimately.
If the attacker knows the internal IP address of your router, can they mount the same attack despite the strong in-system model, or filters it based on IP address?
They can't do it with this, because remember, when you try and do the private IP, it'll fail with this particular attack. If they know the internal IP address, you can try and do anti-DNS rebinding. The downside to that is you have to wait like an exorbitant amount of time, at least in Firefox. It's like 2 minutes or 3 minutes before you can do the rebind. So the realm of practicality starts decreasing there. But yeah, you can also do cross-site request forgery attacks too, but like I said, they're limited. I can't hear what you're saying.
Can't you mount this attack without relying on the same origin policy in the browser? Because you can still do cross-site posts. So you can still do one post request to log in and another post request to reconfigure the
yeah, but not if they're using... okay, so first of all, that won't work on this because it has anti-cross-site request forgery. There's a JavaScript token in there that you have to get. So you can't do that type of attack here. You also can't, like I mentioned, you can't do that against stuff that uses basic authentication. That won't work anymore. So yes, you can use cross-site request forgery, certainly on a lot of routers to do that. The other nice thing about this is because I can see the responses, this also opens up multiple other vulnerability types that are not exploitable with cross-site request forgery, like information disclosure. So for example, DDWRT. By default, when you go to DDWRT's router's page, splash page, it doesn't require you to log in. But it gives me a nice list of all your internal IP addresses and your MAC addresses and the exact build version of DDWRT you're running. And so I can't exploit that with cross-site request forgery, but I can with this. So I don't even have to log in order to get a decent amount of information about your network. And granted, that doesn't give me necessarily a definite exploit, but it's certainly not information that you want to be sharing with everyone on the internet who owns a domain name. So yeah, I'm not trying to disparage cross-site request forgery, and there's certainly a lot of really awesome things you can do with it, and it's definitely an easier attack. But this has several advantages over it, which is kind of the point of doing DNS rebinding. No more questions? Oh. Go back to what? Yeah. What's that? Oh, you just wanted to see the shell? Okay. I know we got one question back there getting a microphone. Do we have a quick one while he's doing that? All right.
Hi, I'm curious about you. With the same origin policy, you mentioned it's built on DNS, which is an untrusted platform. With the changes or motion toward getting DNSSEC more widely feasible, have you would that same statement be true, or could you still do these sorts of attacks with DNSSEC?
Because I legitimately own attacker.com. I've registered it. I own it. So I can set up a legitimate DNSSEC-enabled DNS server for it. Yeah. DNSSEC does nothing to stop this. All right. I can't see anything. We got hands? Yeah, in the back there.
So you said that you tried it on a whole bunch of routers, and I think you said about 17 of them worked, and the rest didn't. Did you have time to investigate the ones that didn't work and figure out why they didn't work and what they're doing there that prevented it?
On most of them, I suspect they're not using the weak end system model. Some of them actually were fairly smart about how they rebound services, so they weren't listening on the WAN port. I didn't get a chance to look at all of them. But from what I've tested, if you're running a Linux or BSD-based system, you're at a much higher risk for attack because they implement the weak end system model in the OS. Now, that doesn't necessarily mean it will work, because there are some Linux-based routers this didn't work against, again, because of the way they bind interfaces and set up their firewall rules. But I mean, if you're running Linux, you're already a third of the way there. And the other two configuration options are actually fairly prevalent. So if you're running some kind of custom OS on the underlying router, it's probably less likely, because interestingly, the weak end system model is more difficult to implement than the strong, because you have to go through and look at all your IP addresses and see if they match, rather than just checking the one IP. Is that it? So yes, there is. The question is, if you didn't hear it, is there anything an ISP can do to help stop this attack? So you notice I'm returning 2 IP addresses. I have seen one really weird ISP that actually would filter out the extra IP addresses. So if I did a DNS lookup on Google, it would only give me 1 IP address back. And that will break this attack. But it also breaks redundancy for Google as well. So it's a pro and a con. Is that it?
Was the deep processing model chosen because of the processing power issue?
I have no idea why they chose that. I really don't. And I suspect it's one of those things they chose before, JavaScript was real big, and you had you had XML HTTP requests and that kind of thing. But yeah, I mean, ultimately, you're trying to enforce security based on a domain name, but the domain name can point anywhere. So it's really just a fundamentally flawed policy, but I have no idea why they chose to do that. Other than it's probably pretty difficult to do it based on IP, especially if you want to allow the DNS redundancy, because then you have to allow it to switch IPs.
Has ActionTech contacted you, mentioning they're going to upgrade their firmware or anything like that?
No, I haven't got anything for ActionTech. Interestingly, though, 2 days ago, a buddy of mine forwarded me an email he got from Verizon saying, we're very secured about our customer security, and here's a link to a website that shows you how to change your default password and all this other stuff. But yeah, I haven't been contacted. The only router company that's contacted me is pfSense, and they're not really a company. They're the open source project. Anything else? All right, awesome. Thank you very much.